Hey guys, I have your notes here for section 10.3, day 3, and this will be the last page of notes for section 10.3. And shouldn't take too long. It's kind of a review, so we're going to go over some of the error bounding, and then I get to show you where Euler's formula comes from. That's kind of cool. But as far as error, when we have a geometric series, keep in mind that whenever we stop our polynomial, we are cutting off several terms. Well, we're cutting off an infinite number of terms if we just look at a polynomial. How far off is that polynomial from the actual function? How far off is it when I cut off all of those extra terms that heads to infinity? So what we do on the geometric series is we look at from the moment we cut off all those terms, that's a different series. So the first term that got cut off all the way to infinity is its own series. So that's the error bound, is what's my new first term for the ones that were cut off over 1 minus r. And again, we're going to absolute value it because we don't want our error to be negative. We just want to know how big is that difference. For the alternating series, keep in mind that your error always has to be less than the next term. Not the whole, we're not talking about all of them, but we're just talking about that very next term. My error has to be less than that. And then, of course, absolute value it, so we don't worry about positive versus negative. And then for our Lagrange error bound, the exact error is found by calculating through this formula. However, we don't often use exact error with the Lagrange error bound because we don't always have an exact value for the n plus 1th derivative. So what we can do is, if we can cap this derivative, if we can say, well, I don't know what the exact value is, but I know that this will never be bigger than whatever. Replace this with that maximum value, and then say my error has to be less than or equal to this. Alrighty, now let's work on Euler's formula. So, you nerds have probably seen Euler's formula somewhere before. It looks like this: e to the ix equals cosine x plus I sine x. And when I sub in pi, I get e to the I pi plus 1 equals 0. I'm going to show you where this comes from. It's not difficult, and it's kind of cool. So first of all, I'm going to start with the series for e to the x. And this little exploration kind of walked me through it. It said find the Maclaurin series for e to the ix. So I start with e to the x. That came from my table. And now I'm going to sub in ix up here. So I sub in ix every time there's an x. And now I'm going to go ahead and multiply everything out. So since this is a monomial, I square each term, cube each term, and so on and so on. And keep in mind that I squared is just negative 1. So this is going to stay in I. This right here is going to turn into negative 1. This one is going to be an I times a negative 1, like I to the first times I squared. So I times negative 1. This one's going to be negative 1 times negative 1, which is going to be positive 1, and so on. Okay, so I replace that with a negative 1. That turns that term negative. Negative 1 and plain I to the first, positive, and so on. Now, notice, some of your terms have an I, some don't. So I'm going to rearrange. I'm going to group all of my terms over here on closer to the equal sign. I'm going to group all of my terms together that don't have an I. And over here, I'm going to group all of my terms together that do have an I. So here are all of my terms that don't have an I, and they keep going, they keep going, they keep going. And then here are all my terms that do have an I, and those keep going, and those keep going, and keep going. Now I'm going, with my second grouping, I'm going to factor out an I. So factor out an I, here's what's left. Then, do you recognize this series? Do you recognize this series? So e to the ix is just this plus this. Now, sub in pi for x. And that's what you get. Euler's formula.